Welcome to Freefall video number 2, where we continue to investigate Do Falling Things Accelerate? Last time on Freefall Physics, we learned by investigating the graphs that resulted from dropping an object in the classroom that the acceleration due to gravity is 9.81 meters per second squared. So we found out that falling things, or at least that falling thing, they do accelerate. They speed up by 9.81 meters per second every second. Well, I think a natural question to ask at this point is, do all falling things accelerate at this rate? What we just calculated to be 976 meters per second squared was one object that we dropped in the lab. But now what we want to do is say that all falling things accelerate at this rate. So is that really true? Now, if you remember at the beginning of the video, we thought about things like a kid jumping off a cliff into the water, a skydiver, leaves, plastic balls that were dropped. Would they all fall with the same acceleration rate? Like, what about if I dropped, say, a physics book and a piece of paper, and I dropped them at the same time? Would they hit the floor at the same time? Well, I think most people would agree that the book would go right to the floor while the paper just kind of drifts downwards. So based on this simple experiment, people for hundreds of years concluded that heavier things, like the physics book, fall faster than lighter things. Why does it look like that? Actually, this is something we're going to be investigating in the class. Well, let's talk about how to apply all that we've learned to word problems related to something that's in free fall. And it turns out that since free fall is just another example of accelerated motion, we can use exactly all these formulas just as we've been using them. The D is going to stand for how far something has fallen. The V average is going to be the average velocity while it falls. T would be how long it takes to fall. V final is the speed after some period of time. So all these formulas are still used with one change, and that change is a big one. A, instead of being anything, now the acceleration is a fixed number. It is 9.81 meters per second squared. So what that tells me is when I am doing free fall problems and I am making my list, if they tell me that the object is falling and I'm making my list of variables, A is now not something that could be anything or something they would have to give me. A is now a known number, 9.81 meters per second squared, which is located on the front page of my reference tables. So let's finish by just trying this practice problem. An object falls from rest, and we're asked how fast is it moving after 3 seconds, and how far has it fallen in 3 seconds. So let's try this. An object falls from rest. How fast is it moving after 3 seconds? How far has it fallen in 3 seconds? So my first job, if you remember, whenever I do physics problems, is I want to make a list. Well, it turns out even this statement here, which appears to have no numbers in it, really has two. And this is what makes free fall problems different. So it says the object falls. So the first thing I'm going to do is write down the acceleration is 9.81 meters per second squared. So I already know that because it says it falls. And it also says it falls from rest. So that means my initial speed is 0. So I already have two numbers, even though there aren't any in this statement. And now the question is, how fast is it moving after 3 seconds? So now they give me 3 seconds. 3 seconds is a time. And the question is, how fast is it moving after 3 seconds? So that's actually a final speed, or velocity, is I don't know. So the initial velocity was 0. Because it's accelerating, it's going to have some velocity after 3 seconds. I have to figure out what that is. So I need a formula that has accelerations, velocities, and time. So that has a distance in it, so there's nothing about it here. That has acceleration, velocity, and time, and so does this. So this has final velocity, initial velocity, acceleration, and time. So I'm going to use this formula. So v final equals v initial plus acceleration times time. So v final will equal 0 meters per second plus 9.81 meters per second squared times 3 seconds. Now if I multiply 9.81 meters per second squared times 3 seconds using my handy dandy trusty calculator, I get 29.43. Now this second cancels out one of those, so I get left with 29.43 meters per second, and that's how fast it's moving after 3 seconds. So now let's do the final question. How far did it fall in 3 seconds? So I'm going to make my list here. So I still write down, still falling, so the acceleration is 9.81 meters per second squared. It fell from rest. The initial speed is 0. It's fallen for 3 seconds. I just figured out that after 3 seconds it's going 29.4 meters per second. So now the question is going to be how far, and that's distance. So distance is I don't know. So I need a formula that has distance and final velocity and time and initial velocity, acceleration. So basically this is kind of like the whole thing here. So I need a formula that's got all the variables, and there's one of those, and that is this one. So let me write this down. So distance equals v initial times time plus 1/2 at squared. So now I'm going to put the numbers in. So I'm going to have distance equals, v initial though is 0. So if I put a 0 in here, 0 times 3 is going to be 0. So actually I'm just going to write a 0 here because I know that that term basically it's going to go away. Plus 1/2 times 9.81 meters per second squared times 3 seconds, which I have to remember to square. So I get my calculator out again, and I square 3 times 9.81 times 0.5, and I get 44.1. And here's how the units work. I'm going to have squared here, or seconds here, but they're going to be squared. So this seconds squared is going to cancel out that one, and all that's going to be left is meters. So that's how far it fell. Now before we stop, let me just show you the most common wrong way to do it, and I'm going to see if you can pick out what's been done wrong. So actually we can learn a lot from the most common wrong way to do it. Again, the question is, an object falls from rest. How fast is it moving after 3 seconds? So we already figured out that's 29.4 meters per second. So sometimes people will come from having figured this number out, and then the question is, how far has it fallen? So people will say, all right, well, the question is, how far has it fallen? And then they'll look at this formula and say, well, distance is speed times time. So they'll multiply 29.4 meters per second, which is what they got from the first part of the problem, times 3 seconds. And they'll get 88.2 meters. And they'll say that that's the answer. But that answer is wrong. Can you see why? First of all, what's wrong is that this number, 29.4 times 3, would be how far you would go if you were traveling at a speed of 29.4 meters per second for 3 seconds. But I'm not going 29.4 meters per second for 3 seconds. Doing this results from a wrong understanding of what acceleration is. What actually happens when I accelerate is I start at a speed of 0, and only after 3 seconds am I going 29.4 meters per second. So actually this number is way too big because I only hit this speed right at the end of 3 seconds. Before 3 seconds I'm not going this speed. So I actually am going a lot less distance than this. And where did that mistake come in? That mistake came in because this is not my speed, it's my final speed. And this formula, distance equals speed times time, is wrong. This formula says average speed. So if I put an average in there, average of what? Average between the speed you started out at and the speed that you finished at. So the average of 0 and 29.4 is half that speed. So this number actually needed to be the average of 29.4 and 0, which is half of 29.4. So that's why this number is actually twice as big as the correct answer of 44.1.